So now I want to review these modular arithmetic computations that we have learned how to do, namely solving linear congruences and solving systems of congruences in the sense of Chinese remainder theorem. And I'm going to review these by actually doing a new sort of problem that we have not seen before. So, let's say we are given a system of linear congruences. So, the Chinese remainder theorem tells us what to do if we have something like this. But now I want to ask, what if it looks slightly more general than that? So let's say we have something like and what's another good okay, let's say this is our system. So do we know how to solve a system of linear congruences like this? And the difference, just to point out again, is that if we only have one equation, we know how to solve this in the style of a linear congruence. And similarly, if we get rid of these coefficients, we know how to solve this using the Chinese remainder theorem. But how do we solve this more general problem? And the answer is that, well, it's basically just using both of them. So the idea, geez, I need to be able to write here. Idea translate into Chinese remainder theorem problem using what we know about linear congruences. So what I mean by this is, let's review how we solve a linear congruence. So remember, I want to draw this analogy with solving a linear equation, which is to, if this were an equation, we would solve for x by dividing both sides by 2. And in this context, in the context of modular arithmetic, we know that we can't do that in exactly the same way, but the idea is that, i.e., since 2 and 3 are coprime, which means their GCD is 1, there is an inverse. Ooh, what is that word? Inverse for 2 mod 3, i.e. an integer A such that A times 2 is congruent to 1 mod 3. And in general, find inverses using the Euclidean algorithm to find Bézier coefficients, because then that looks like a times 2 plus b times 3 equals 1. And here you can see that a is an inverse for 2, because if you take this equation mod 3, this becomes a 0, and you just get a times 2 congruent to 1. That is what it means to be an inverse. But, so this is how you can do it in general. This will always work. But for small m, we can just do it by inspection. So what do I mean by, what I mean by this is just look at it. Or, really just check a couple of things. For example, if you're working mod 3, do you really want to use the whole Euclidean algorithm to find Bézier coefficients when instead there's 3 things to check and you could just check all of them? So, I mean, there's even less than 3 things to check, because 0 is never going to be the inverse. So it's got to be 1 or 2, and you can pretty clearly see that it's going to be 2. So inverse for 2 mod 3 is given by 2, because 2 times 2 is 4, which is congruent to 1. And now, what do we use this inverse for? Why did we want to find this? The point is that if we multiply both sides by the inverse, two times 2 times x, okay. If we multiply both sides by the inverse, then we get an equivalent congruence. So x is going to solve this exactly when it solves this. And this side, what multiplying by the inverse does is it gets rid of this coefficient and just makes it x congruent to 2 mod 3. And now you can see that 2 is a solution. But, okay, so this is linear congruences. Now let's go back and see how this allows us to solve the original system that we had. And let me actually take this down with us. Cool. Actually, yeah, let's put it over here. Okay. So, what we just found is we considered this equation individually as a linear congruence. And we saw that it's the same as saying x is congruent to 2 mod 3. So you can see that if we can do that with both of these congruences as well, then we will get something that looks like the situation where we can apply the Chinese remainder theorem. So let's do that translation real fast. So what is an inverse of 4 mod 5? Well, again, let's just check some things. Is it 2? 2 times 4 is 8. So no, because that's 3 mod 5. Is it 3? 3 times 4 is 12, which is also no, because that's 2 mod 5. Is it 4? I think it is 4, because 4 times 4 is 16, which is 1 mod 5. So let's multiply both sides by 4. The left side, it cancels out and becomes an x. On the right side, 4 times 3 is 12, so it's 2 mod 5. And then similar here, inverse of 3 mod 4 is 3, I think, because 3 times 3 is 9, which is 1 mod 4. So again, let's multiply both sides by 3, and we get x congruent to 3 mod 4. So now you can see that this is in a form where we can apply the Chinese remainder theorem. And we will do that in just a second. But I want to make a note that has come up a couple times now. Inverse of A mod M is not always A. So we see this a lot. But basically, it's just because we're working with very small moduli, very small m. So for example, mod 3 and mod 4, it is true that everything is its own inverse, but that's just because there's almost nothing to work with. For example, mod 3, 1 inverse equals 1. I mean, this is always true. And then you only have one other thing besides 0, but 0 doesn't have an inverse. You only have one other thing, and so its inverse has got to be the only other thing as well, which is itself. And mod 4 is exactly the same. 1 inverse equals 1. 2, remember, you have to be coprime to the modulus, so 2 is not going to be invertible either. So the only other thing is 3, so its inverse has to be the only other thing, which is 3. Let's see. We start mod 5, I think you start to see examples where it's not always that. So 1 inverse, let me put little congruences here since we're working mod something. 1 inverse is 1 as always, but now 2 inverse is not 2, because 2 times 2 is 4. 2 times 3 is 6, which is 1 mod 5. So these things are inverse to each other. And then 4 is, the only thing left. But you can see already here that it is not always the case that the inverse is the thing you started with. But people have asked about this many times, and for good reason, because it does happen coincidentally a lot of the time. So you can see that here, coincidentally, I mean all 3 of these, coincidentally, the inverse is the same thing, but it is not always true. So let's, okay. Let me put that to the side, and let's return to our Chinese remainder theorem. And this process is a little bit longer. So let me think if I should do the whole thing or just give some comments. So I think let me try to explain again why it works, and then I will blow through the execution. So the idea is that it will be nice if we can solve these separately and then assemble them into a solution. And we can basically do that. Solve separately, and then combine. But some extra steps to avoid, what should we call it? To avoid interference. So essentially, maybe you can think of it, if you want to think of it slightly differently, as we're not really solving, so let's take the first one. We're not really solving this independently, but we're making it a little bit easier on ourselves by changing the rest of them to zeros. I guess I have this in the other order, so I may as well keep the same order. And then for 5, we do a similar thing. And why don't I just write it out all the way? So we're sort of solving these 3 problems independently when we solve the Chinese remainder theorem. And you can see now that if we set it up like this, if we have something that solves these 3 equations, and we have another thing that solves these ones, and another thing that solves these ones, if we add them together, it will solve this system. Because mod 3, it will be 2 plus 0 plus 0, which is what we want. Mod 5, it will be 0 plus 2 plus 0, which is what we want. So we're sort of setting this up specifically so that it gives us a solution to the whole system when we just add them together. Let me erase all these extra marks. And then for each of these individually, we write, so solution is 2, so let me make some symbols here. So this 2 is that 2. It's the thing that you want it to be modulo the particular equation you're focusing on. And then you multiply this by 4 times 5. So let me give this a round circle, because these are the other moduli that you want to avoid. But then, you're no longer going to get this thing if you change your solution. So you have to change it back. So you multiply by inverse of 4 times 5 mod 3. So then this is ensuring that you get the zeros here and here. And these 2 cancel out, mod 3, so you get the thing you wanted there as well. And once you have this system, once you have this outline, you can see that all you need to do is find an inverse of 4 times 5 mod 3. So let's do that real fast. So 4 times 5 is 20. And 18 is a multiple of 3, so this is 2 mod 3. So inverse is 2. So from this term, we get 2 times 20 times 2. Okay, so for the other 2, let's not do all of that talking, but let's just say, what do we need to know? We need an inverse of 3 times 4 mod 5. So this is 12. So 12 is congruent to 2. Inverse is 3, as we saw over here. So let's just take this immediately down and see what the contribution is. it should be the thing we want to get mod 5, then 3 times 4 to knock out those moduli. So let me just say 12. And then it should be the inverse to get rid of this change. And then the last one, what do we need? Inverse of 3 times 5 mod 4. So 3 times 5 is 15. That's congruent to 3 mod 4. And the inverse is 3. So that gives us the thing we want to get mod 4 times the product of the other two moduli times this inverse. And now we're basically done. We just need to add it all up. And all right, you know what? I'm not even going to bring out a calculator for that. You're allowed to on the exam use a calculator to do your arithmetic, but we can do this in our heads, right? This is 80. This is 6 times 12, which is 60 plus 12, 72. And this is 6 times 15, which is that 100? It's 60 plus, what's 6 times 5? 30. Is it 90? It's 90. And then 80 plus 70 plus 90, so the left digit is 2. What's 8 plus 7 is 15, plus 9 is 4. And then carry 1, equals 7. Oh wait, 15, 24. I think it's this. My arithmetic is correct. It is this. And remember, so the Chinese remainder theorem tells us also that a solution to this kind of congruence, to this kind of system, is unique modulo the product of the moduli. So we can take the solution and add any multiple of 3 times 4 times 5, which is 60, I believe.
You made a mistake for the 3 times 15 times 3.
Oh no, really?
Yeah.
Oh, it's 9 times 15.
Yeah.
Jeez. What's 9 times 15? Help. 9 times 15 is
135.
135. Yeah, that sounds right. Okay. I am absolutely going to get out a calculator. Okay, 287 is my new guess. Hopefully that tracks with what you'll have known. Total of 287. Yes, awesome. Thank you. Cool. So, with your help, we have managed to solve this Chinese remainder theorem problem. And in fact, we have also learned how to solve systems of linear congruences without ignoring these coefficients like we normally do in the Chinese remainder theorem. So, I think that is our good review of solving the various types of congruences.